Hello, welcome to this presentation. My name is Francesc Lordan. I'm a researcher at the Barcelona Supercomputing Center, and today in this talk I will be introducing Colony, an ongoing project that I have with my colleagues Rosa, Badia and Daniele Lezzi. Besides explaining the key concept behind the project, I will also present the preliminary results that we have achieved so far with our prototype implementation, and I will describe all those challenges that we haven't been able to tackle yet and that we are looking for some partner that helps us with them. To better understand the motivation of the project, we should take a look on how distributed systems were used. Traditionally, users would submit an isolated execution of the application and, leaving apart tailored solutions like the ones using MPI, most of the frameworks were selecting one node of infrastructure to become the master. This node was decomposing the application into several tasks and orchestrating the execution of such tasks on top of the other nodes of the infrastructure, the workers. Another important feature was the reliability of the network. Except for sporadic disruptions, the infrastructure was stable and only changing under controlled circumstances like, for instance, when the master decided to scale in or out. Lately, the Cloud-Edge Continuum has arisen as the new dominating paradigm for distributed computing, since it encompasses all the other new kinds of deployments, IoT, swarms, fog, edge, cloud, including those models considering the mobility of the devices, such as mobile edge computing and mobile cloud computing. The main feature of this paradigm is to consider a global view of the infrastructure, including all kinds of compute devices, starting from the server nodes in a cluster backing a cloud service to smartphones or onboard computers in cars, passing through the intermediate devices composing the network like antennas or cell stations. In addition, the infrastructure is aware of how close our devices one from each other, thus allowing everybody to benefit from this technology. Application users have access to a larger compute infrastructure, service providers have new business opportunities due to the lower latencies of the network, infrastructure providers have a lower energy bill, and the rest of the world benefits from lower carbon footprint. In this kind of environments, we envisage three types of computation. The first, batch computing, refers to the classical usage of a distributed system where an end user requests an application execution. However, changes in the infrastructure or data may also trigger computation, and here we have identified two new scenarios for computing. On the sense-process-actuate scenario, the infrastructure has to react to some external event to compute a proper response. For instance, a sensor warning a high level of water in a dam. On the other hand, we have the stream processing case, where a data source continuously produces data that needs to be processed at real time. For instance, image recognition from a camera. This paradigm is totally the opposite to the traditional approach for distributed systems. First, multiple devices may trigger a computation at the same time, and not only trigger the execution, but also this execution can spawn new tasks. In the end, all the devices of the infrastructure have to behave in a similar way as a traditional master did, but the responsibilities now are shared across all the devices. Besides, mobile devices may easily lose connections and change their locations. The infrastructure has to quickly react to these changes and readapt to the new setup. Due to these changes, the traditional frameworks for distributed computing no longer give an efficient response to the challenges set by these environments. For that purpose, it is necessary to build new solutions that deal with them. In this slide, we show the fundamental decisions that we took while designing Colony to face each of the problems. Since computation may be triggered by any node in infrastructure, even mobile devices that can get isolated, the first decision that we took was that devices should always be able to end executions. For that purpose, our solution is based on a standalone software component deployed on each device. We call this component agent. To allow multiple requests at a time, we propose using a function as a service model. Thus, any device can request to its agent the execution of a function whenever the application requires. Moreover, to deal with the hardware heterogeneity of the system, this function should be serverless and assume nothing from the hardware hosting the execution. The agent will select the best way to run the function given its local computing devices. With virtualized environments like containers or VMs, we aim to deal with the software heterogeneity and the possible problems of sharing devices by several users. To achieve a higher performance and a better resource usage, we propose to convert the code of the functions into task-based workflows. Thus, the function could carry out the computation in parallel using cold embedded computing devices, and could offload part of the computation to remote agents to avoid the resource scarcity. For handling the infrastructure dynamicity, each agent should provide a mechanism to change the pool of resources where it can run tasks, and also implement some fault tolerance mechanism to recover from network disruptions that twofold the infrastructure. The last problem that we aim to solve with Colony is the complexity of developing applications for these kind of environments. Currently, sense-process-actuate computations are supported with function-as-a-service solutions. There are specific frameworks for stream processing, and large parallel computation require using either domain-specific solutions like MapReduce, Spark, or AI frameworks, or general-purpose workflow managers. To ease the development of these kind of applications, we aim to offer one single programming model, able to support both task-based workflows and data flows. For testing purposes, we used COMPSs on our prototype. To take a deeper look onto our proposal, we will start with the cornerstone of the project, the agent. Even when isolated, an agent should be able to receive a function execution request, convert it into a task-based workflow, and run it in parallel on its locally embedded computing devices, like CPUs, GPUs, FPGAs, or any other accelerator. For achieving this purpose, the agent presents the following architecture. Through the agent API, it receives the function execution request. Currently, this API is available through REST and a proprietary protocol based on sockets to enhance the performance. Upon the reception of the request, the API submits a task that encapsulates the execution onto a runtime system. The purpose of such runtime system is to handle the execution of tasks on a pool of resources while guaranteeing that dependencies among tasks are fulfilled. To achieve this purpose, the runtime has 4 subcomponents. The first subcomponent is the resource manager, which monitors the currently available resources. When the node is isolated, the only available resources in the pool are the compute devices embedded on it. The second component is the task scheduler, which plans the execution of pending tasks on the resources provided by the resource manager. When the task scheduler decides to run a task on the local compute devices, it contacts the data manager, a component whose purpose is to store and share data values. The task scheduler fetches from the data manager the necessary values to run the task, and then it contacts the fourth component, the execution engine, which controls the execution of the task on the local compute devices. Finally, when the task starts executing on a local device, the programming model acts, detects nested tasks, and requests their execution to the runtime system. So an agent can offload tasks onto another agent. The only thing that needs to be done is to add the remote agent into the resource pool of the first one, indicating which protocol should be used to interact with it, REST or the proprietary protocol. Then the task scheduler will consider offloading tasks onto that agent and submit tasks only if it's worth it. To modify the resource pool, the agent API has methods to add resources, remove them waiting for already submitted tasks to end, and remove a node considering that all the tasks that were offloaded there and are still running have failed, and then the task scheduler will resubmit them onto another node. Taking into account all the resources from the infrastructure is a heavy computational burden for the task scheduler. To simplify this problem, we propose to organize the infrastructure resembling organic colonies, groups of autonomous individuals that get together to achieve a higher purpose, in this case reducing the compute time to provide a better user experience. Devices belonging to a colony are autonomous agents capable of processing information. The members of a colony offer their embedded resources to run functions in a serverless, stateless manner. In exchange, they receive a platform where they can offload their computation. Each colony selects one of its members to become its nexus. All the regular members of the colony are configured to have only one remote node, the nexus, that has the resources of the rest of the colony. Regular members will offload the computation onto the nexus, which is the only node configured to interact with all the regular members. The nexus acts as the workload balancer within the colony. The nexus also acts as the interaction way to the outside of the colony. All external agents willing to offload tasks onto the colony need to contact the nexus, and the nexus is the only member of the colony allowed to offload computation outside of the colony. In turn, to avoid overwhelming the task scheduler of the nexus, colonies are allowed to be divided recursively to reduce the size of the scheduling problem. Thus, infrastructures can be organized in a hierarchic way like the example of this slide. An additional advantage of colonies is their ability to rapidly adapt to infrastructure changes. By only redefining the interconnections of the nexus, whole colonies can be handed over. For instance, in the example of this slide, all the devices within the personal colony become part of the home colony only by changing the smartphone connection. To evaluate our proposal, we conducted experiments using 2 use cases. The first one is a classification service. With it, we wanted to validate the behavior of colony on 2 of the computing scenarios. We used the inference of the model to set up an experiment for the sense-process-actuate scenario, and the training of the model to illustrate the case of a patch job. The testbed for this first experiment is composed by 21 nodes divided in 3 big colonies. A cloud colony composed of 11 nodes with 48 CPUs each and hierarchically organized to match the topology of the cluster backing this cloud. And then 2 more twin colonies representing 2 fog organizations connected to the cloud. Each of these colonies is composed of 5 nodes, a fog node with 24 cores, and 4 edge nodes with 4 CPUs each. Within each fog colony, 2 of these edge nodes run a JMeter instance that simulates a varying number of users owning a sensor that notifies an event approximately once every second, according to a normal distribution. When JMeter emits readings corresponding to 10 users, the edge nodes receiving the request can host all the workload. No tasks are offloaded. When the number of sensors increases to 100, the edge nodes can no longer host all the workload, and they offload part of this request onto the corresponding fog node. In one of these cases, the fog node cannot host all the workload and offloads part of them back to the edge nodes of the colony, without sending any of them to the cloud. Finally, when 300 users submit requests, the fog colonies have not enough resources and offload most of the computation to the cloud. Thanks to the system's ability to balance the workload, the response time slightly changes. For the second experiment, we trained a random forest model submitting a batch job request to the nexus of the cloud colony. In this case, we measured the execution time when increasing from 1 to 32 the number of nodes within the cloud colony. In the random forest algorithm, the problem size grows linearly with the number of estimators. In our implementation, each estimator training requires 2 depending tasks and about 6 seconds to execute. The top chart shows that for all problem sizes, Colony is able to improve the execution time as infrastructure grows. However, looking at the second chart, we can see that the efficiency of resource usage is poor on large infrastructures. In this case, there are 2 reasons for that. First, as the infrastructure grows, so does the workload imbalance. The second reason for that is the application tasks are too fine-grained for COMPSs and this size of infrastructure. To fill the whole infrastructure, Colony should be submitting a task every 2 milliseconds, and it takes longer than that for COMPSs to detect and submit a task to the Colony runtime. Finally, the third experiment corresponds to the second use case. For this one, we wanted to validate the ability to deal with the stream processing, and we used a real-time video processing application. In this case, the testbed was smaller. There was a Raspberry Pi with a camera and a quad-core laptop. The application processes every frame and identifies the people on them to create an activity report. For each frame, COMPSs creates the workflow depicted in the leftmost part of the slide. When running the application sequentially using only the Raspberry Pi, the system took 41 milliseconds to process each frame. With Colony, the compute-intensive tasks were offloaded onto the laptop, leaving on the Raspberry Pi only the collection of the frame from the camera and its serialization to ship it to the laptop. In this case, a frame was taking only 353 milliseconds. Thus, Colony achieved a frame rate improvement from 0.024 to almost 2.8 frames per second. So, to wrap up this presentation, let me highlight the important messages. First, the paradigm shift in distributed computing requires the creation of new programming tools to develop applications for the Cloud-Edge Continuum. Among these tools, there's Colony. The second important message is that there are 3 different types of scenarios that require computing on the Cloud-Edge Continuum, and through COMPSs, Colony is able to support the 3 of them. The cornerstone of the Colony project is the agent, which allows applications to request the execution of serverless functions in a service manner. The ability to convert the logic of such functions into a workflow is the most important contribution in this work, since no other function as a service tool supports it, and it allows to parallelize the applications to reduce the execution time, exploit the hardware heterogeneity of the devices, and distribute the workload across the whole platform. Finally, the concept of colonies allows a reduction of the scheduling problem and exploits the low latency of nearby resources. As already said at the very beginning of the talk, there are some open challenges that Colony needs to tackle before being considered a complete solution. We are already working on some of them, and for others, we are willing to find somebody with whom we can collaborate to resolve them. The first problem on what we're currently working is enabling the detection and management of multiple levels of nested tasks. Detecting these inner tasks allows achieving more parallelism. Besides, given the hierarchic nature of Colony, the management of these inner tasks will be totally transparent to the agent handling the parent task. This allows to distribute not only the computation, but also the management overhead of these tasks. Other problems that we need to face are dealing with how the agent containers are deployed on the nodes, and how to automatically attach new nodes to the hierarchy. For the task scheduling, we also aim to do some research based on game theory and quality of service parameters. Finally, a very interesting problem is the data management. On the one hand, we are willing to explore new mechanisms to share data values while guaranteeing the intellectual property, privacy, and militarized parts of the infrastructure. On the other hand, we are also looking for mechanisms that enable the automatic distribution of data monitoring to trigger computation. I really hope that this talk has awakened your interest in the Colony project. If anyone in the audience has any questions, I'll be pleased to answer them now. Otherwise, this is my email address. Please feel free to contact me to solve any further doubts that you may have in the future, or to propose any collaboration opportunity that you might be interested in.